Hi folks, welcome to our review for quantitative skills. Today we're going to be reviewing the multiplication principle, combinations, permutations, probabilities, and then discuss just a little bit on exponential and linear growth and how that all works out. So without further ado, we're going to get started, and if you have any questions along the way, there's a chat box appearing on your screen there. Please go ahead and just type in that question into that chat box during the time we're covering a problem, and I'll be happy to answer it once I see it pop up there. Okay, so without further ado, let's get started. We have a secret code for a bank consists of 2 letters, then 3 digits, then 3 more letters. How many different codes are possible assuming the letters are not case sensitive? So not being case sensitive means capital A and lowercase a, they would be considered the same. It's just an A. Now let's think about this, and what I always like to use is just some underlines, so we'll just put those in here. So we have letters, and I'll denote that underneath by L, and then we have 3 digits, which we'll denote by D, and then finishing off with 3 letters, so we'll denote those by L again. Now thinking about this, we could choose any letter in the alphabet, so we could put A in this first coordinate, and notice we could follow up in our second little blank here with another A. We could choose B, we could choose C, we could choose any letter in the alphabet, and there's 26 letters in our alphabet, so that means we have 26 possibilities for that first position. The same goes for the second position. As we said, we could repeat, so that means we could have 26 there. And since these are steps to a sequence essentially, so we're picking one, then the next, and it matters what order we're picking them in, we can use the multiplication principle. So moving forward from there, now we move to the digits. Well, how many digits are there? Well, there's 10 different digits, and so you might be thinking, what? But you got to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so that makes 10 in total. So we have 10 digits, and then we can repeat those digits for each position. Okay, and then we finish off with letters again, and notice there's 26 different letters. Okay, and so we can keep on going there, keep on going for all those positions and get our final answer. Now this would be acceptable either method. You can write that as 26 times 26 times 10 times 10 times 10 times 26 times 26 times 26, or just 26 to the 5th times 10 cubed would work just fine. Now if you wanted a number, let's see if I can pull up a calculator here. So this might be slightly too large for the calculator, but that's okay. What you can do is do 26 to the 5th, which, oh, let me make sure here, hold on one second. So we have 11,881,376. That would be just 26 to the 5th, I believe. And now if we tack on the 10 cubed, well, that's going to just toss 3 more zeros at the end. And so this is the number of codes for our final answer. Questions on that? Once again, if you have any questions, please ask them as we're going. So let's expand upon this idea. Determine the number of possible codes if the letters are case sensitive, and we're basically seeing, does this make a big difference? Well, the number of slots remain the same, and notice we have letters in the first 2, digits in the second 3. Oops, did I put one extra? Yeah, I guess I did. Sorry about that. And then we have letters in those last 3 positions. So when you take a look at this one, what happens? Well, how many letters are there possible if we are case sensitive? Well, we had 26 lowercase letters and we have 26 uppercase letters. So that means we have 52 letters, and so where does that 52 come from? If you add 26, so this is lowercase, and 26 uppercase, notice that makes 52 letters possible. And so that means in our first position we have 52 possibilities, and the same goes for our second position. Now the digits has not changed whatsoever. We're talking a single digit. And then our letters, once again, we can have repeats, and so you get 52 in every single position. So notice this makes, if we take a look, the only change is instead of 26, we get 52 to the 5th times 10 cubed. And now, taking a look at 52 to the 5th, we're getting even larger here. So this is equal to 380. And so what I'd recommend doing is doing the 52 to the 5th. You get 380,204,032. But with that 10 cubed, that's going to tack on 3 extra zeros right there. And so that's the number of codes in that case. So notice when we allow for upper and lowercase, we've just drastically changed the number of codes possible, right? So we went from what was it before, 11 billion to 380 billion essentially. That's a big jump right there, and that's why when we're practicing codes and things like that, it's better to have different cases represent different things. It makes things more secure for us. So moving forward on that one, let's start to see some different sorts of approaches on problems. There are 5 different positions on a basketball team, and if a team has 11 players, then how many different lineups can be made? So you don't have to necessarily know basketball. What we're talking is a lineup. This could be lineups on so in terms of people forming a line in a class. Say you have 11 people in a class and you want 5 people to form a line. Same thing. If you have 11 songs on a CD and you want to line up 5, and you want to pick your favorite 5 from there and line them up in order on your own mixtape. That's well, mixtapes are out of date now, but hopefully you get the idea in terms of what's going on. Now, for those of you that don't know, it's not a big ordeal, but there's 5 positions on the basketball team, right? There's a point guard, a shooting guard, a small forward, power forward, and a center. Okay. So now let's talk this through in terms of how many players could we choose to be the point guard, assuming every player can play every position, right? In that case, it would be 11 possibilities. But now, let's say we have Sherry playing point guard, right? So Sherry couldn't play any of these other 4 positions. So that means, if Sherry's already been accounted for, we only have 10 players left for the shooting guard position. Okay. So we have 11 and 10 there. Now, say we had Sherry and John playing point guard and shooting guard respectively. Then we move on. How many different possibilities do we have for small forward? Well, that means you have 9 players that could possibly play small forward. So, for example, and I remember I said Sherry, John, let's say Abe played small forward, and then we're going to have 8 possibilities for the power forward. So let's say this is let me pick a different letter. Kate. So Kate is our choice in that position. And then last but not least, let's do Leon. So we have 7 there. Okay. And then there's what? 6 players remaining. So Gabe, Pat, Ben, Yolanda. So that's 4. Rico and Dennis. Okay. So out of our 11, we chose our starting 5 and in those positions. Now notice that would be different, a different lineup. Say we still had those remaining people on the bench, but say we just changed John and Cherie. This is a different lineup. And that's important because what's happened here is the order in which we list them, the way in which we arrange these people, that makes a difference. And the idea here, yeah, granted, we can get an answer. So we take 11 times 10 times 9 times 8 times 7, and we get our 55,440 lineups. But with that in mind, what we've actually done here is something called a permutation. Okay, we've taken a set of 11 people, and then we chose basically our 5 people to be in there. Now the formula for this, if you don't recall, we take this 11 factorial and we divide by 11 minus 5 factorial. Okay, so this means we have 11 factorial over 6 factorial. And so the way we can actually cancel this off, we can write 11 factorial as 11 times 10 times 9 times 8 times 7 times 6. And then we can do times 5 times 4 times 3 times 2 times 1, but 6 times 5 times 4 times 3 times 2 times 1 is just 6 factorial. So the 6 factorials will cancel here. And notice we're left with the same answer that we got using the multiplication principle. Okay, that's hunky-dory and makes things all nice for us, right? But what I want us to be able to distinguish is that, hey, this is a permutation because order is important and we do not have repeats of players and positions. Okay, keep that in mind. That's going to cut down our time because we can just put P11, 5 and have our answer. And sometimes these numbers will be so large we can't even handle what the final answer would be. So now let's take a look as to how many different groups of 6 balls can be selected from a barrel containing balls numbered 1 through 67. Okay, so think of this as the lotto essentially, right? Let's say you had a ticket. So here's your lotto ticket. Okay, so you have your lotto ticket, and on your lotto ticket you have 3, 7, 13, 58, 59, and 64. Okay, and so let's say here's our bin, and coming out from this bin, let's say they draw. And let's say they drew 7, 13, 64, 59, 58, and 3. Would you be happy if that was your lotto ticket and that's what they drew out of that bin? Of course you would, right? You had a winning ticket, and so everything's hunky-dory. You win millions of dollars and life is good, right? However, let's take a look at another possible scenario. So let's say instead of drawing them in that order, what happens if they drew 58 first, then they drew 59, then they drew 64, then they drew 3, then they drew 7, and then they drew 13. Do those still match the numbers on your lotto ticket? Well, yes. And so you still be happy. You don't care which order as long as all the numbers match up, right? You still win millions of dollars and everyone's happy, right? So the key here is order is actually not important in this case. It didn't say, hey, they had to be selected from a barrel in a certain order. No, it just said, hey, select it from a barrel, right? So what essentially has happened is order is not important. This deals with what we call combination. Kind of showing you the long way what can happen. So first off, you can think of, okay, let's say we have 6 spots, right? Notice you have 67 for the first ball, and then we can't draw that ball again, so you get 66 for the second position, 65 for the third, 64, then 63, then 62, all right? So now, though, moving forward, how can we actually deal with this because we don't have order being important? Well, for each grouping, you have 6 elements. And so let me just say A, B, C, D, E, F, right? Now, for example, what we could do is we could do A and then C, B, D, E, F. That would be the same grouping, but that's counted extra times here, right? It's counted as something different. Same thing when we did, if we do A, C, B, D, F, E, right? So how many ways can we order 6 elements? Number of ways to order these, because that's what we're going to have to divide by. So the number of ways to do that is 6 factorial. And so that's what we're going to divide by there. So at the end of the day, what do we have happen? Well, you have the 67 times 66 times 65 times 64 times 63 times 62. And you want to divide that by the 6 times 5 times 4 times 3 times 2 times 1. And so what you're left with, oops, that should be equal, sorry, is 99,795,696, and that's our final answer. That's not the only way to do this, though. As we mentioned, it is a combination. Okay, so there's a couple different ways to write this, and so don't let the notation fool you. Mathematicians get lazy, so we find these shorthand notations. One method is to write the C, and then we have a set of 67, and we want to choose 6 of those elements. Or another method that people might like is something like this, where you have a 67 on top of the 6, no fraction bar or anything there, but you get something like this. Now, what does this mean? One way of looking at it is this P676, so that's the permutation that we talked about, and we divide by that last number as a factorial. That's essentially what you just saw, right? Because what we have is this is 67, we got to just write our 6 spots, 67 times 66 times 65 times 64 times 63 times 62, all divided by 6 factorial. Okay. Questions on that? Now, the other method, too, the way we can write it as well, notice if I start by writing it this way, right there is the permutation, and then we can slap on an extra 6 factorial and have our answer. Okay, but really what we're boiling down to is order important or not? Right? That's really what the question boils down to. If we can answer that, we're in good shape. And that's what we'll take a look at on the next one. So how many rearrangements of the letters heart can be made? So notice if we're dealing with that scenario, so we can't repeat the letters, right? Because we're rearranging them. And let's think, there's 5 letters, so and so let's say we have first 5 times 4 times 3 times 2 times 1. Now the question is, do we divide? Well, so let's say we have H-A-E-R or H-A-E-T-R. Okay, is that going to be different than A-T-R-E-H? Yes, these are different. So since these are different, and we can't have any repeats, that tells us that order is important. Okay, so then we have, what does this equal? Well, I believe that's just 120, right? 5 times 4 times 3, so that's going to be 60 right there, and then times 2 is 120. Oh, and there's 120 rearrangements, I should make sure. And on the last one, I should also make sure. And your answers, you're just going to need to put the numbers, but that many groups is what we're doing. Okay, moving forward. City Council with 9 members must elect a 4-person committee, and then how many committees are possible? Well, if you're taking a look at this, what are we going to have to do in this case? Well,